Well, hello again, everyone, and welcome back to the Traffic 21 Mobility 21 University Transportation Center Deployment Partner Consortium Symposiums Research and Education Showcase. The Mobility 21 team is a tight collaboration among Carnegie Mellon University, the University of Pennsylvania, the Ohio State University, and the Community College of Allegheny County. We come together to increase our reach and scale of all four of these institutions. Tackling the multifaceted nature of Mobility 21's objectives requires coordinated technology and policy activities and is supported by researchers spanning multiple disciplines: engineering, computer science and robotics, public policy, urban design, information systems, and data analytics. The Deployment Partner Consortium associated with us is represented by public agencies, nonprofit organizations, private sector companies, and other research institutions. We also have a distinguished advisory council of national leaders that help provide strategic guidance and counsel. We are happy you're joining us today to hear about the research and academic efforts that are happening throughout our University Transportation Center. We will be hearing from 5 different presenters during this hour, and then we will be going into breakout rooms where we will be able to have smaller size conversations with the folks that have been presenting. So the 5 topics that you're going to be hearing about is hearing about using LGSVL and Apollo simulator to assess HMI needs while in self-driving mode. And I'm sure Helen's going to tell us what all of those initials mean. Improving short-term travel speed prediction with high resolution spatial and temporal rainfall data. Pedestrians on the roadway. What the heck is a choice rider anyway? A theoretical framework and empirical findings from the Philadelphia region, and leveraging data sources to assess effects of mileage-based user fees in Pennsylvania. So first, I'm going to stop sharing my screen and ask Helen Loeb from the Children's Hospital of Philadelphia, who also works with the University of Pennsylvania, to tell us more about her work. Helen?
So here I unmute myself and I'm gonna share my screen. Hopefully
Correct.
This is good. So you tell me if you see my screen, it should say drive right. Do you see that?
Not yet.
Not yet. Okay. Okay, yes, I think I need to click here. That's why. Share. Okay.
There we go.
Okay, wonderful. Thank you very much, Lisa K. And I actually apologize. I realize you mentioned Lisa K, that all these letters that appear in the title of my talk, my presentation. It's actually very, very simple. What I'm interested in is the interaction between humans and machines, and in terms of driving, self-driving. How is it going to work out for people to be comfortable using these vehicles? So this project is a collaboration between Rahul Mangaram from UPenn and myself. I'm talking with my startup hat. It's a small company that we have in Philadelphia called Jitsi. But as Lisa K mentioned, I've done a lot of work from the Children's Hospital of Philadelphia side in human factors in self-driving. So I'll move to my first slide. So we know everybody's out there developing algorithms, developing vehicles. And what I found as a researcher, and I come from robotics as well, but I love, to think about people and how it's going to work out for people. So what I found is that there is an insufficient amount of work that is being done about how it's going to work out for people. And I guess I'm thinking especially about the older people and also people living with disabilities, which possibly have never been driving. And you can see on the right, like a shot from Saturday Night Live, their view of self-driving. So, this is what's in people's mind, in the PAVE, which is a coalition that's working off Washington, just had a study, and constantly we have 50 to 70% people who do not trust self-driving and would never set a foot in a self-driving car. Something else that I want to highlight is here we have something that comes from Tesla. We know Tesla is a leading company in terms of deployment. The number one reason customers visit Tesla service center isn't because something is wrong with their car, but because they just don't know how to use them. So clearly there is a need to facilitate this transition, and that's what we are trying to do. So I've been working with driving simulation for the past 8 to 10 years. I've had over 100 people come and sit in our driving simulator, from the job side. And we are now developing what we call augmented mixed reality driving simulation that can be very, very immersive and allow people to be comfortable, not to be taught anything and know exactly what to do, so that we can assess their level of trust. So this is going to be a native car environment with very light and affordable sensor. And what we're hoping for is maximum immersion. So I'm going to show you here two views of two different prototypes. So on the left, you see a Honda minivan. So we use kind of a green screen technology to present on the screen of the Honda, a self-driving view, a view of a scenario. And we are doing the same thing on the right side with a Toyota Prius. So what the work that Raul and I are doing is both on the hardware side of things and the software side of things, preparing a platform so that we can bring people in and assess their level of trust in the technology. But also at the same time, we are preparing to put together a dashboard of what is the information that's necessary for people to be comfortable with the driving self-driving mode. So for this, we use Apollo, which is AutoWare. This is on the driving side. So we, at the same time, at the same time, we offer a platform to test people, but at the same time, we also study what kind of information is necessary for people to be comfortable with the technology. So for this, we use AutoWare, we use Apollo, and what we want to do is be able to bring people in, show them for example, when they are going to pass a car in self-driving mode, what information do they need to be comfortable with the way the vehicle is operating? If there's going to be an emergency stop, if the car is going to change lanes all of a sudden, why is it? What information is needed to make people comfortable? So I guess what Raul and I are doing is putting together this platform so that we can welcome people of all ages and all driving levels to come, learn, sit down, and be comfortable with the technology, so that they are comfortable going out there and say, well, I'm ready to get it for myself now. I'm ready to try the autopilot on the highway. I'm ready for that, even if that's somebody who is 70 years old, 75 years old, and would not be comfortable at the very beginning. So I guess, do I have more time, or is that good? I want it to be rather brief, so.
Wow, Helen, you did an awesome job. You still have a minute. You have one more minute?
Okay, great. Great. So we are located in Philadelphia. We have been welcoming students from pen. And yeah, we are very actively developing. So the main aspect of the technology, which is there is a patent attached to it, is the mixed reality, augmented reality. It relies on the ability to combine in a person field of view elements that are real, that would be your real car, yourself, maybe your passenger, and elements that are virtual, that would be anything that's outside the car. And that allows us to like program these scenarios and immerse people into this, like pretend like they should think they are driving, even though they are safely, you know, sitting in a stationary car. So that's the objective of the project. So thank you for the opportunity to present, Lisa Kay.
Oh, and thank you so much for being here. And we will have time to have more discussion with you, so hang on the line. But please stop sharing your screen at this
point.
And
so
that way, Corey,
right there.
There you go. And Corey will start sharing his screen. He's going to be sharing with us his work on improving short-term travel speed prediction with high-resolution spatial and temporal rainfall data. Corey? Okay, we can see it great.
All right, hey everyone.
There you go.
Presenter mode. So hey everyone, Lisa Kay said my name is Corey Harper.
And Corey, let me stop you for a second. You're very quiet. Can you?
Okay, sorry. Let me see. Now?
Oh, much better. Thank you.
Okay, all right. So hey everyone, my name is Corey Harper, and today I'm going to talk to you about a project that I recently did over the past year, where I incorporated high resolution rainfall data into a travel speed prediction model with the hopes of improving active management of the transportation system. And the reason why we did this is because of climate change, right? And due to climate change, we've seen a lot more heavy rainfall events in the Pittsburgh region, right? So what this graph shows is that in 2018, this was one of the wettest years in the city of Pittsburgh, right? And when heavy rainfall occurs, this causes flooding in the road network. One of the issues is that we really don't know these things beforehand, and we usually find these things out when we're at the dinner table, we put on the news, and then we see which roadways have flooded, right? And if we don't know this ahead of time, people could drown and there could be gridlock in our transportation network. So what we're trying to do here is predict ahead of time what travel speeds may look like, so that we can divert traffic or maybe close roadways before any safety issues occur. And in the past, a lot of hydrologists have tried to do this work, but what we do is take a data-driven approach to look at this issue from a different perspective. So this is our study area. This is Allegheny County. Our target segment in green was Washington Boulevard. We chose this roadway because, as many of you may know, in Pittsburgh, this roadway tends to flood a lot, and people have drowned this roadway. So we thought it'd be a good case study for our tool that we're developing. And you also see some alternative routes, some highways, some other main intersections and arterials. But the unique thing about this study is the data, right? So this data comes from the Three Rivers Wet Weather Organization. We have 33 rain gauges scattered throughout the Allegheny County region. You see the rain gauges in yellow there. And then we have gauge adjusted radar rainfall data, right? So this data provides an estimate of rainfall for every 15 minutes for every 1 kilometer squared area in Allegheny County, right? So it's really high resolution. And what most studies do is they have one rainfall gauge, right? So where you see this red square is by the Pittsburgh airport, right? So most studies use a rain gauge from the National Weather Service. If I was going to use that one rain gauge, this where you see the red dot is where the rain gauge would be, and I really wouldn't have any more information. And I would assume that the rainfall here the rainfall here can tell me what the rainfall is anywhere else, right? And what we're hoping that is by including this additional rainfall data, we can develop a more accurate prediction model. So this is just an example of a rainfall event that occurred in the Allegheny County region on January 11th and 12th, right? And in the red, you see high rainfall amounts, right? So in your top left corner, there's a lot of rainfall, and in your bottom right corner, there is a lot less rainfall that occurred, right? So the point is, if you don't have this high resolution rainfall data, you're going to be missing a lot of information that could inform your model. So one of the things that we did in the study was that we group rainfall data by wind direction, and we did this because, so in Pittsburgh, the southwest wind direction is the prevailing winds in the region, right? And we did this because we're building a machine learning model, right? And it's really hard to discern why the machine learning model picks some rain gauges over another, right? So we needed a way to discern why they were picking these, right? And also rain clouds travel with wind, which likely means that these rainfall features will be the best predictors of rainfall in our network 30 minutes from now. And this shows a subset of features that were actually included in our prediction model, right? And we did this to reduce overfitting and improve model performance, right? We have thousands of rainfall features. We can't include all. So we include the most important rainfall features, as well as the most important speed features that would provide us with information to help us predict travel speed 30 minutes from now in our target segment on Washington Boulevard. So that's what you're seeing here. And what we're seeing is that in Washington Boulevard, especially during moderate and heavy rainfall events, we're able to achieve better predictions when using this high resolution rainfall data, right? And right now you're seeing about a 4% improvement during these events, right? So we go from about 18.9 when you're using a single citywide rain gauge to about a little under 18% when you're using the high resolution rainfall data, right? So that's about a 4% improvement, right? And I know a lot of you might be saying, well, you did all this and it doesn't seem to be substantial, right? But the thing is, even small improvements in traffic safety could provide huge benefits, right? So for example, there were 900,000 crashes that occurred in 2018 in inclement weather. Even if you address about 0.1% of these crashes, you could see over $160 million in cost savings annually. Right, so here's some policy implications. So flood warning alerts from the National Weather Service are very generic. Future broadcast messages could be more detailed, letting drivers know which roadways to avoid and which roadways to shut down. Currently, Washington Boulevard shuts down when water accumulation on the roadways reaches a certain threshold. What if we could shut down roadways and redirect traffic before waters reach dangerous levels? And as you saw before, societal benefits can be substantial as we avoid a lot of crashes that occur in inclement weather events. So thank you, everyone. That was it.
Corey, thank you so much for sharing that information with us. And now we're going to kind of switch gears and go to the Ohio State University, where Umit Ozguner is our director of the UTC for OSU, and he is going to be telling us about his project, Pedestrians on the Roadway. Umit?
Actually, I do believe it's Dongfang. Is he logged in?
Yes.
Okay, so it's really Dongfang is a graduate student about finishing his PhDs, and he'll be the one that will be presenting.
Okay.
Okay, thank you everyone. And now I'm going to share my screen. Okay, so is my screen visible?
Yes, we can see it.
Okay, yeah, thanks. So today I'm going to give you an overview of one of our recent work that belongs to the UTC Mobility21 project. So this is about dealing with pedestrians on the roadway and modeling the vehicle-pedestrian interaction. So the material that will be presented here today is based on one of our recent publication in the Intelligent Vehicle Symposium this year. And if you are interested in this work, you can also go to our GitHub repository, as we have open sourced all the code for this simulation framework. And you can also take a look at the video demo of our simulation. So for this work that I'm going to present, basically we have developed a simulation framework for the vehicle-pedestrian interaction in the uncontrolled pedestrian crossing scenarios. So the scenarios is illustrated in the first figure, and in the scenario, the pedestrian would like to cross a road at a place where there is no traffic signals and there is no zebra lines, and the vehicle needs to somehow react to the crossing pedestrian so that the collision should be avoided. And the second figure shows a real example. And in this example, the pedestrian is kind of jaw walking. So it comes out of somewhere in the road, and the vehicle needs to somehow properly react to this jaw walking pedestrian. So, and to achieve this simulation, we need to consider both the pedestrian's motion and the vehicle's motion. So this framework will specifically model the motions of both the pedestrian and the vehicle. So why are we doing this? So the reason of doing this simulation framework are threefold. So the first concern is pedestrian safety. And if you look at the third figure here, and this is a statistic from the NHTSA report, and it says the percentage of the pedestrian fatality over the total fatalities in the traffic crashes from 2008 to 2070. And as you can see here, the percentage of the pedestrian fatality in the total fatality has been increasing over the past 10 years. So this is kind of counterintuitive, but it is a fact. So that means that although our technologies has been improving over the past years, but we are somehow ignoring the pedestrian safety issue. So that's one of the reasons of creating this simulation framework. And the other motivation is that nowadays people are making advancement in the automated driving areas. So for an automated driving system, usually we need to test the algorithms that is developed for the automated driving system. But for those algorithms, they require lots of testing and verification. But when an automated driving system is dealing with such a pedestrian crossing scenario, it is difficult to do real experiments, as this kind of scenario is difficult to create. And it is very rare, but once an autonomous vehicle meets such a scenario, it is very important. So that's why we want to create such a simulation framework to kind of test the algorithms before a real implementation, real experiments. And the last motivation is that, in fact, we also want to create some unusual scenarios, which is hardly ever been seen in the real world. So that's the last motivation of this work. And basically, for this framework, we kind of proposed a 3-layer framework. And so for both the vehicle and the pedestrian, they all have 3 layers. And 1 layer is responsible for the perception, and the perception layer is kind of responsible for sensing the environment. And after sensing the environment, the second layer is called the interaction layer, and which is responsible for making decisions and generating actions. And once we have the actions, the action will be sent to the last layer, which is called motion layer. And the motion layer will basically describe the physical motion of either the vehicle or the pedestrian. And here for pedestrian, we have a 3-layer architecture, and for the vehicle, we also have another 3-layer architecture. But due to the time today here, I will not go into the details of these layers. But generally speaking, for the pedestrian, in the perception layer, there is a gap estimation module, which estimates the time gap. And the time gap is defined as the time for the vehicle to go from its current position to the crossing position. And for the motion layer of the pedestrian, it's basically a point mass dynamics, and it receives a virtual force as an action, and the virtual force will change the pedestrian's motion accordingly. And here for the interaction layer in the middle, the pedestrian it basically has a higher level decision making and a lower level microscopic force generation. So the higher level part is kind of like a state machine, and it describes the steps of the pedestrian gradually approaching the road edge, judge the time gap, and decides to cross the road immediately or let the vehicle go first, something like that. And the most important decision here is whether to cross the road immediately or let the vehicle go first. And this is achieved by judging the time gap with a gap threshold value. And this gap threshold is drawn from normal distribution. And this introduces.
Excuse me, just want to give you a 1-minute warning.
Oh, okay. I'm sorry, this might be too complicated, so I will just skip this part. So for the vehicle, it's similar thing. So we have a perception module, and we have an interaction module, and we have a motion layer module. And here for the interaction, we have tried 3 different controllers, and we want to compare these controllers. And I will skip these slides, and I will just show you some quantitative results here. So using this vehicle pedestrian interaction framework, we can basically achieve the simulation something like this. And in this case, the pedestrian yields to the vehicle, and in another simulation results, the vehicle yields to the pedestrian. So by this, what I would like to express is that the simulation framework can generate reasonable vehicle pedestrian interaction behaviors. And we also conducted a quantitative evaluation, and it also basically evaluates whether the vehicle behavior and the pedestrian behavior is reasonable or not. And by showing the reasonable vehicle pedestrian interaction behaviors, we can somehow concluded that our proposed simulation framework is effective. So that's basically what this work is doing. And sorry about the delay. And yeah, that's basically what it is.
Yeah, that's very helpful. Thank you. And we're going to have time for a lot more discussion in our breakout room. So keep the presentation handy. And we will come back to it. But for now, I'd like to ask you to stop sharing your screen.
Okay, yeah, thank you.
Yes, thank you. And Eric Guerra from University of Pennsylvania. oh, you already shared your screen, is going to be telling us about what is a choice rider. Eric?
Thanks so much, Lisa Kay. Good afternoon. Excuse me. First, I want to acknowledge a few master's students who have worked with me on this project, Andrew Wong and Han Chiao. The term choice rider first enters the lexicon in the early 1960s. Here's just an example of the Pittsburgh area transportation study from 1963. It's a term that's always used in opposition to other terms like captive rider, necessity rider, dependent rider. Captive rider was particularly popular in the 1970s and has been almost entirely replaced with the term dependent rider. The term primarily comes into use with the public takeover of previously privately operated transit systems, and it's a way to characterize transit user markets. And it's used in government reports about transit and textbooks and even some journal articles. In addition to some pervasive and circular definitions, like a dependent rider is someone who depends on transit, these are some of the keywords that show up. I'm just going to emphasize a few. A choice rider is car owning, is white, is a man, lives in the suburbs, and a captive necessity or dependent rider is a racial minority. They're carless. They have short trips in the center city, and they rely on bus as opposed to rail. The broader uses and implications, one is that transit riders will use transit no matter what, so you don't really need to plan for them or focus investments on them. And you really need to get people out of cars, so you should focus investments towards choice riders. This is how it's used in the early literature. And therefore, transit investment should focus on high capacity transit to support white, suburban, wealthy, car-owning workers with downtown jobs. That's kind of a summary of how it's used in these early reports. Don't have time for kind of the quotes, but you can see they're pretty concerning. The academic literature hasn't really moved far from these early definitions, although I will say that often in academic work, there's a kind of a conclusion that it might be bad public policy to focus investments on so-called choice riders instead of dependent ones. That said, after 50 years of use, the term really has no strong theoretical or empirical definition. And as a result, maybe a poorly conceptualized and unmeasured term has encouraged investments in wealthier, whiter, and more suburban, to benefit wealthier, whiter, and more suburban households. Take a pretty simple research design, use utility theory, and basically I say that a choice rider is someone who has close to a 50% probability of choosing transit. I use a random utility framework, just estimating a binomial logit model, and it's the choice between someone taking transit and using a car. Samples is use data from the Philadelphia region. Is relatively high transit use. It's sometimes referred to as the biggest poor city in America. It's very high use of its urban bus network. It also has substantial commuter rail service into wealthy areas. The term the main line has become synonymous with the wealthy western suburbs. Just a little information on the predictions. We're predicting with some socioeconomic variables, trip characteristics, environmental characteristics, all things that are associated with transit ridership, and also associated with some of the terms that are associated with choice and dependent transit riders. Predictors of higher transit use, just a few of them listed here. I'm not going to get into this in much detail, given the time that we have. And this is a cumulative distribution of the probability of choosing transit over a car. And I'm going to focus the rest of this on this kind of 40 to 60% probability of choosing transit. So this is really the definition that I use for choice rider. Two approaches. I'm just going to use the first right now. I have some slides on the second one, but I'll save them for the breakout session. The first is just to compare people who have a probability of 40 to 60% of taking transit over a car. These choice riders are substantially likelier to be poor. They're substantially likelier to be non-white. They're substantially likelier to have lower education, although there is a high distribution of graduate degrees, which I think is related to the number of research institutions, universities, and hospitals in Philadelphia. They're also much more likely to be carless. Carless people are not transit dependent, and much more likely to live close to downtown. I don't have a slide for this, but they're also much likelier to have better transit service There are very few people choosing to use transit where there's poor service. In short, an actual choice rider looks a lot more like the stereotype of a captive rider that's long biased transit planning documents and academic writing. Again, I'm not going to have time for this, but there is a lot of variance in what a choice rider looks like. And I just give a few examples of their trips and who they are. But I want to jump right to the conclusion and a few takeaways for practice. So popular professional academic characterizations of choice riders are almost certainly inaccurate. And a reconception of choice ridership based on theoretical and empirical grounding would tend to encourage investments that improve services for poorer minority households living in more central urban areas. This likely also has environmental benefits because these people, if they don't have good enough transit service, are almost certainly going to drive. So in terms of drawing people out of cars, this is also the best place to focus transit investments. And a few kind of brief takeaways. I know a lot of people who work as transit planners and transit operators know this. And for these practitioners, I really hope that these empirical findings provide them a piece of evidence that they can use to kind of make their arguments. And then for practitioners and academics that still make the distinction, I really think it's important to get rid of the term dependent rider entirely, or captive rider. No one is really captive. And in fact, a lot of the things that we associate with being captive are signs of being a choice rider. And in order to get people riding transit, we really need to provide high quality service. So I probably came in under 5 minutes. It was quite a number of slides. So I wanted to go through it quickly, and I look forward to talking about it more in the breakout discussion.
Thank you so much, Eric. And one of the least favorite things I have to do is to give people time checks. So I appreciate you were right there on time. So thank you for that. If you can stop sharing your screen, we will have Scott Matthews start to share his screen. And he is from Carnegie Mellon University and is going to be telling us about his project, leveraging data sources to assess effects of mileage-based user fees in Pennsylvania. Scott?
Yep, and I assume you guys can see the slides.
Yes, we can.
Great. So thanks everyone for your patience in this session and getting to my last quick overview talk before we do breakouts. As Lisa Kay said, this is a big team project, and in the interest of time, I'm just going to point at the list of participants who are in multiple departments, both the civil and environmental engineering and the engineering and public policy departments here at CMU. And we've been working on thinking about several projects related to the transition that is upcoming to mileage-based user fee or road user charge systems with a focus on passenger vehicles. And we come about this in a couple of specific ways. What we want to do is study the data flows that are going to be needed that will further enable such a deployment to systems like this in Pennsylvania as well as in other states. There's a couple of interesting facets to this problem. There are certainly some data analytics issues, there are economic issues, and there's also some really interesting policy analysis issues. And so we have a team of people interested in all those things that have been assembled and made some initial progress, and we hope to continue making some more progress in the next year. And what I'll largely be doing, and they are posted on them, and thank you to Lisa Kay for linking them both on the page that everybody was provided, summarizing the results of 2 papers that we submitted to the annual Transportation Research Board conference that we look forward to talking to people about. But please feel free to check out the papers also. I'd also, of course, like to mention our partners that we've been working on with this project, CompuSpections, which is a data provider that I'll talk more about in a minute, another connected company called Data Driven IM, a mileage-based user fee technology company called Ozguner, and the Mileage-Based User Fee Alliance, which is a consortium of states and technology providers and others interested in this transition that we're going to be talking about. So let me make sure that everybody understands what we're saying here. What we've mostly been doing to date since cars came around is paying for transportation through gas taxes on a $1 per gallon basis. There are federal gas taxes, there are state gas taxes, the federal funds augment the state funds. But if you didn't know this, the federal gas tax rate, which is roughly 20 cents a gallon, has not increased since 1990, so for 30 years. So aside from the issues of inflation and construction costs going up over time while the revenue isn't, states have had to start making up some of those differences by increasing the state shares of gas taxes to get road projects done. In addition, on top of that, there are issues associated with highly fuel efficient vehicles not paying as much not paying as much per year, since they use less gallons of fuel and thus pay less in terms of dollars per gallon. So there's many drivers for talking about trying to fix or improve a funding system that doesn't just involve continually increasing dollar per gallon rates. So what is mostly seen as what's going to happen is a transition from this pay by gallon to pay by mile kind of framework. And which is where you get this idea of mileage-based user fees. This is a direct way of charging for use of transportation. In our work, we've been focused on the passenger fleet, but there's certainly efforts that are going on to do the same thing for commercial trucks. We're just not looking at that. It's not that hard to do, right? You need a technology to track the mileage in some way, and probably location if you want to have very specific rates to account for, you want to account for whether people are already paying for gas taxes, and if so, credit for that, and figure out a fee structure. And we've been looking at all those things in our work. Some states have already done pilot programs, and it's generally shown the technology is there and this can work. And some states have even moved from pilots to formal programs. So if you're not familiar with this, this is something that is absolutely being worked on in many places in the US and around the world. An interesting challenge that we've been finding is this idea of the state transportation expenditures is actually pretty complex. And Pennsylvania, which I will not go into in this session, but in the breakout perhaps, has a very complicated transportation funding formula where money comes in from sources and it's paying for many, many other things. The concern is if you try to completely just replace what's the so-called gas tax share, it's still not going to be enough to pay for everything. And so if you're going to switch to a mileage-based fee system, switch to any system, you want to make sure it's going to have enough funding to pay for everything you need. And this is really what we're noticing is overlooked by many states, partly due to data problems. We've been looking at various data sources such as the highway statistics data. We have data on annual emissions from safety and emissions inspections in Pennsylvania from various sources, as well as registration data. So we can see through lots of data analytics and algorithms how much cars are driving of different types on a per year basis. So what we've found, and we can talk in more detail later about, is that this idea of setting a fee is easy. But what you would find is that if you're just using it to replace gas taxes, you're going to undercollect the funding you need, the revenues you need to pay for all of the things that transportation funding has been diverted to. And the federal data, such as the highway statistics data, is not very consistent and also not very helpful, as I'll say in a second, in terms of trying to do this. And you could actually get around it by having very complex fee structures, but that might not be what a state wants, right? So trying to do things on a per road, per county, urban, rural basis, which is easily feasible, is going to be a very complex system. And so that's another big challenge. I wanted to leave you with one sort of hypothetical example here, which is we did analytics on the entire passenger fleet in Pennsylvania for the last 10 years, lots of analysis. And if you wanted to say, at the end of the day, we want to completely replace just gas taxes with this idea of a mileage-based user fee, instead of having the so many cents per gallon fee that we currently have, what we would do is say that we'd probably be charging about 2.5 or 3 cents a mile on average in the middle. You can see this sort of heat map of counties that would be paying slightly higher, slightly lower rates based on how many miles per year those cars are driving. Of course, those counties just tend to have cars that drive a little bit more. But that's the ballpark we're talking about. We're talking about moving through a system that instead of paying $250 a year in gas taxes, you're paying 2.5 cents a mile. The data sources would otherwise tell you, based on how much money we spend in Pennsylvania, that we'd need to be charging 7 to 10 cents. And so we've been really trying to get into what the crux of those discrepancies are so that we can continue to work on that to states. We're planning on building some spreadsheet and decision support tools so the states can see what those discrepancies are and that we can continue to help them see what technical hurdles need to be overcome. So in closing, we're interested in finding anybody else, including deployment partners, who are interested in doing these kinds of things in Pennsylvania or other states. So thank you, Lisa Kay.
Thank you so much. I am going to put my screen back up just to give everybody the list of presentations that we heard today.